Today we are going to discuss a very interesting topic. Why interesting, you might ask? That's because it involves science. And I know a lot of you might hate science, but it is the foundation of each and everything. It is logical, a lot of concepts are involved, and this topic in particular might take you back to school, ninth and 10th class. And obviously, it is a high possibility that many of you intelligent people are already aware of the science and the concept as a whole that we are going to discuss. So I am at an advantage, rather, you will be able to catch up with me, not find this topic entirely boring, and maybe correct me if I err somewhere. So let us begin. So basics of remote sensing. So definition क्या है? No matter what you say, if you're a student of science or any subject, rather sociology or anything, you need to be able to express yourself clearly. So remote sensing, if we divide it into two terms, to define anything, just break it into parts. So remote refers to far distance, like we talk about remote places. We have the TV remote. So without touching the TV, we are actually able to change the volume. We are actually able to change the temperature of the air conditioner. Okay, so same. And sensing, we are sensing or detecting something. In case of geography, or we can say astronomy, remote sensing is the science. It is essentially the science of collecting information about, I'm just writing the keywords, the Earth's surface without direct contact and with the help of components known as sensors, which can be attached to satellites, aircrafts, drones, or even ground-based platforms. Okay, so this is, now you got the two concepts, remote sensing and what is a sensor. So I think this is absolutely clear. So just to give you a perspective of things to come, so I have just put a few collage, a mosaic of some of the famous satellites which are used commonly in remote sensing. So we have MODIS. This is moderate resolution imaging spectroradiometer. Then this is Landsat, very popular. Normally, whatever work we do in geospatial analysis or geoinformatics systems, Landsat satellite images we use a lot. Then this is Copernicus. Landsat is NASA's, Copernicus European, and then we have our very own IRS. The sensor which is used here is commonly LISS. IRS, Indian Remote Sensing Satellite. LISS is Linear Imaging Cell Scanning Sensor. So all of these are satellites. They use specific sensors to detect the radiation. Okay, so we'll come to that. I'm talking about radiation and all this stuff. So first of all, just a basic overview. We have discussed what is a sensor, what is remote sensing, some examples of satellites. So basically two major types of sensors are there. Okay, active, this is active and this is passive. Okay, you might remember active and passive voice in English. Okay, we'll not go into that. But basically, as you can see, passive means that this sensor depends upon the energy of an external source, most commonly the sun, to detect the radiation through reflectance from the objects on the earth, such as trees, water, buildings, settlements, and then it communicates with the station, on ground station. In case of active remote sensing, as you can see here, this generates its own energy. The satellite or the sensors, they generate their own energy which reaches the ground objects, get reflected, is detected, and then communicated to the ground station. So obviously this is much more advanced, but it is more expensive also. So there are other differences also, but basically one more important difference, that obviously since it is dependent, the passive sensor is dependent upon an external source of sunlight. So at night it's a problem for this is not such a big deal for this. So basically what happens is, for reflection, just remember some words I'll be explaining. For reflection bands, for detecting reflection, okay, for detecting vegetation, settlements, such stuff, we can easily use the passive. But when the surface reflectance, the reflectance is not sufficient to detect, then active sensors have to be used. Most commonly, they are in the form of microwaves. Okay, whenever microwaves are being used to detect any feature on the surface, then most commonly these are active. So examples are radar, lidar. So the satellites which I showed you earlier, MODIS, Copernicus, Sentinel, and Landsat, LISS, these are all examples of passive. Of course, Sentinel also has 1 and 2. One uses radar, so it is active. But for imaging, most of the imaging that we do of the surface, land use, land classification, land use, land cover classification, they are dependent, they are passive. Sentinel 2, you might have heard of. Okay, so there are various such components. Okay, now important basic concepts. You might already know this, but still, it is important to understand. So, first, we are going to discuss about the electromagnetic radiation. You know all this, but can you tell what exactly is this? So, electromagnetic radiation is, or electromagnetic wave, is a form of energy. It is self-sustaining. It travels through space and consists of oscillating electric and magnetic fields. Okay, so you remember these keywords, you connect them and form a definition. Okay, so this is what the radiation look like. A lot of concepts are associated with it. We are not going to go deeper into that. You might know about photons, the dual nature, okay, the particle, and most common expression, if you have remember physics, q q is equal to h mu, that denotes the representation of energy of a photon. Q is energy, h is Planck's constant 6.626 into 10 raised to the power minus 34 joule per second, and nu is the frequency, or we can write it as hc by lambda also, a common expression. Okay, so c is the velocity of light, and lambda is the wavelength. So you can see, and one word you might have come across many times, transverse. Okay, so what is transverse wave? Basically, in this, the oscillation of the particles, if a wave is going in one direction, the oscillation of the particles, or the electric field or magnetic field in this case, it takes place perpendicular to it. So here you can see, if we treat this as direction of the wave propagation, see, the particles are not actually going, okay, so they are oscillating up and down. Or, so if we take this as the x-axis, so we can say electric field is oscillating along the y-axis, and the magnetic field is oscillating along the z-axis. Fine, so this is electromagnetic wave. Some important concepts which you can remember. Okay, now what is this? This is known as electromagnetic spectrum. So when you assemble the entire combination of different wavelengths of electromagnetic radiation in a particular order of frequencies or wavelengths, what you get is electromagnetic spectrum. Okay, the various wavelengths. So in this case, normally you might have seen, okay, so here you can see in the figure, the wavelength is increasing from left to right, and the frequency is decreasing from left to right. Okay, so normally wavelength and frequency are inversely proportional to one another. So if I draw a graph in this, okay, so here we can say in the gamma rays, the waves will appear very close, just an illustration. And here if we talk about radio waves, then they will be far off. So here wavelength is the distance between crests of two consecutive crests, distance between two consecutive crests or troughs. Okay, and here the distance is less between the crests and troughs, so wavelength is less, but more number of crests or waves are passing a particular point in 1 second. So that is the definition of frequency. So frequency here is high, wavelength is low. Here frequency is low, but wavelength is high. This is a basic concept you have to remember, even if you have forgotten it. Okay. So now we know there are multiple components. You already have heard of this: gamma rays, X-rays, UV rays, then visible light, Vibgyor, rainbow, something interesting comes to your mind, infrared radiation, radio waves. Okay, lot of wavelengths. Now, one just a reference, because in the diagrams which you see on the net, a lot of times you get confused, because although it is not necessary to remember the exact range of the wavelengths, but you need to have a slight idea in order to understand the subsequent concepts. So I'll give you an illustrative table. So if I start writing the wavelengths and the component of electromagnetic radiation and the corresponding wavelengths, so it goes like this. So if we take only we select only a few important wavelengths. So UV rays, wavelength normally 10 nanometer to 380 nanometer. Nanometer, you know, 10 raised to power 1 nanometer is equal to 10 raised to power minus 9 meters. Then we have the visible light. This is 380 nanometer to 750 nanometer. Then we have infrared. Now infrared is also subdivided into further categories. So first we have the near infrared. So this is approximately 750 nanometer to 1400 nanometer. Then we have short wave infrared. This is approximately 1400 nanometer to 3000 nanometer or 3 micrometer. Okay, you multiply this difference of 1000 nanometer, 10 raised to minus 9, micrometer is 10 raised to minus 6. Okay, then you have thermal infrared. It also is classified into several mid wave, long range infrared, but the general criteria, this is 3 micrometer to 1 millimeter. Okay, then we have the radio waves. Okay, radio waves, again you might encounter different categorization of radio waves. Normally, from what I understand, is radio waves are categorized into microwaves, okay, which are the normal constituents of what? Active remote sensors. Okay, and radio waves and so sometimes, mostly radio waves, they are also categorized as, both of these are categorized as radar. Okay, so radar, they normally, microwaves, they go for from 1 millimeter to 1 meter, and radio waves, they go from 1 meter to several kilometers. Okay, so in radio waves you have AM, FM, frequency modulation, amplitude modulation, EV, TV signals, Wi-Fi. So all these. Now the categories, if we see this UV, will forget for a while. These are very important in the case of remote sensing, because whether the sensor, what we detect, the reflectance I was talking about, the light which is reflected by the vegetation, by land, by the objects on the ground, they this three types of reflectance bands or reflectance wavelengths, they are detected by the sensors attached to passive satellites, passive sensors of satellites such as Landsat, Sentinel, LISS, okay, MODIS. Now, this we'll not discuss for today. TIR, basically, these bands are associated with emission. These are two different concepts. Please don't confuse them. Reflection is basically the bouncing back of the light after hitting a surface. So, in simple words, the sunlight is here, it comes down, it bounces back. So, this is reflection. So, whenever sunlight is hitting, it contains all these spectrums. So, what the sensor does is, sensor receives the reflected light, it analyzes all these components and then detects or transforms the signal into further images. Okay. This is dependent upon the emission. For example, emission can happen only when energy is absorbed. Okay. Here in reflected bands, we are assuming that no energy is being absorbed. So if nothing is absorbed, it cannot be emitted. Okay. So here, this band is normally used to determine the thermal conditions, the heat contrast of oceanic bodies, water bodies, the vegetation, land. You might have come across this term UHI, urban heat island. So for detecting or determining the characteristics or the spread of urban heat island or analyzing it, collecting data for this, for temperature, for this, we need this bands. This For this, the reflectance bands will not come into use. But our focus for today is this reflectance. Okay. Before we discuss that, one interesting topic is the resolution. Resolution, and another term is pixel. You might have heard. So pixels are what you can see. So you can easily tell me which is a high resolution, which is low resolution. So this is low resolution, this is high resolution. So definition क्या है? Basically, whatever digital images we observe on our screens, on our TVs, phones, laptops, they are formed by a combination of grids or squares. This is known as pixel. If I want to define it in one sentence, simple sentence, a pixel is the smallest element of a digital image which corresponds to a particular value. In a particular image, like if I say that neutrino is the smallest component, one of the smallest component, it cannot be broken further. So similarly, in a particular image, there is nothing beneath pixel. Pixel is the ultimate element. Okay. And what is resolution? Resolution, in case of remote sensing, resolution is the ability of a sensor or a particular display system, like we have HD TVs, HD laptops. So it is the capability of that sensor, or in case of a particular display device, the capability of the screen to display 2 pixels clearly. Okay, so this low resolution in this picture, the pixels, the display is not able to combine it into a proper image, not able to differentiate. Okay, here it is much smoother. Similarly, this I have just put an illustration that, for example, you might have heard earlier, you might have heard of this resolutions. Okay, 144p or 480p, that small Nokia phones when they started coming initially, even TVs also. So this is the standard definition SG. Then above that 1280 into 720. Okay, so this is HD. Okay, then we have Ultra HD, QHD, then we have 4K also. Okay, so we'll not go into detail. So basic is this: pixel, smallest element, and resolution, the ability of a sensor to distinguish or separate two pixels. So higher the resolution, clearer the image. Okay. Now I've already talked about reflection. We'll restrict our discussion to reflection, mostly reflection, although I've mentioned in brief emission, but I don't want the concepts to get confused. Okay. So we have discussed about remote sensing, sensors, some satellites, how the active and passive sensors work, the categories, the categorization of the images. Okay. Then this is the actual what I have been talking about. So just pay attention. So what happens is the reflectance now is detected by the satellite, but that is not the end of the story. Why? Because when radiation is coming from the sun and reaching the earth, then it encounters atmosphere and its particles, it encounters dust, water molecules, oxygen, nitrogen, soot, haze, clouds. Okay, so all these. So when this they collide here with these particles, light or the radiation gets scattered. What is scattering? Again, scattering, unlike reflection, scattering is the redirection of light. Okay, in reflection, most commonly what happens is there is incidence. This is the normal. This is the light ray. So theta 1, theta 2. So normally we have studied, like in reflection, we see our reflection in the mirror. Theta 1 is normally equal to theta 2. So this is reflection. Reflection, again, if I discuss an extended concept, it can be of two types: specular and diffuse. So specular normally takes place into polished, smooth or calm surfaces such as water. Okay. Diffusion for rough surfaces. So here in smooth, calm surfaces like polished roads or asphalt plain roads, the light is coming and getting reflected. Here the light is coming and getting scattered into. So both these reflections, they contribute to the detection, to the radiance which is reaching here. Okay. So before we discuss further concepts, let me introduce some more. Now we are going to get a little more advanced into concepts. So some terms which we need to know about. Irradiance. Okay. Irradiance, if you know insolation in geography, so you can say that is, it might be similar. So basically irradiance is the energy which is reaching the earth's surface. Okay, similar to insulation, it is expressed normally as E is equal to d phi by dA. Phi is the flux measured in watts and dA is the measure of area over which the energy is falling. So its unit will be watt per meter square. Okay. Then we have the concept of radiance. Radiance is basically the energy which is detected by the satellite after reflection. Okay. So this is radiance, this is irradiance, this is radiance. Now its unit will be watt per meter square steradian, or to simplify I can write watt meter minus 2 steradian minus 1. It is basically like this, watt upon this. Now what is this SR minus 1? Okay, so SR minus 1 is steradian, or the representation of solid angle. Okay. So basically, when the reflected light is going back from the surface of the earth towards this, so you can see here, can see an area. This area is actually a three-dimensional space. Normally, what we consider when we find an angle is we take a circle, two-dimensional, and we find out this. But here you can see the surface is not flat. From the area where the information or the reflection or the radiance is collected, it is not flat. So what we need is a three-dimensional angle to enable the sensor to detect the radiation properly. So we need the solid angle. Okay, so this is the importance of solid angle. Okay, so radiance is represented commonly by L. Okay, then we have spectral radiance. Okay, spectral radiance now divided into two. Radiance, we know this. Spectral, we have already discussed the electromagnetic spectrum. So spectral radiance is the energy or the radiance which belongs to a particular wavelength. Okay, so for example, we want to know what is the radiance or the energy associated with the red wavelength of light which is reaching the sensor. So that will become L lambda. In that case, we'll include the wavelength component also in this. So watt per meter square, says steradian raised to -1, and micrometer -1. Normally wavelengths are measured in micrometers. Okay, so this is then reflectance, another important, because in normally whenever we are studying scientific or geographical concepts, nothing is absolute, it is relative. Okay, nothing is an absolute reflector, not even your mirror. So reflectance is basically the proportion of energy which is being reflected by a particular surface. For example, now if we relate all these concepts, for example, 100 watt of energy is reaching a surface, say water or tree or some building, road, but that surface is reflecting or sending back into space only 80 watts. Other may be converted into heat, or it may be absorbed, or it may be scattered. So here the reflectance value is 80 by 100, 0.8. So high reflectance value, you can relate it with albedo. Okay. So snow, ice, glaciers, they will have high reflectance. Trees, vegetation, water, they will have low reflectance. Sand, bare sand will have high reflectance. Okay. So this is the important concept. Now we come to this. Now this is interesting. So what happens is, so when the radiation, here you can see the symbol also L lambda. These terms, if you allow me, I'll discuss. So what happens is the radiation which is reaching here, okay, the sensor, okay, but the job is not yet done because sensor also has limitations. We cannot say, okay, sensor, I'm sending this joules or watt per meter square, okay, please record it. No, it's a type of a computer, it's a type of machine, it has its limitation. It needs a system or a proper algorithm to record its data. So it records first, how it records its data, DN, digital number. So we have talked about pixels. So whatever energy is being reflected by these objects on the ground or earth, it is being recorded initially by the sensors in the form of pixels expressed as bits. Okay, bits. Computer bits, bytes. It something strikes a chord. Okay. So it the brightness levels of the pixels, they are stored in the form of bits. Now, how many bits and how many levels, that depends upon the number or the advanced nature of the sensor. So initial part or the when the technology was not very advanced, normally 8-bit sensors were being used. So 8-bit means 2 raised to power 8, 256. So 0 to 255 levels of brightness can be. So now you can see nowadays there are sensors like 2 raised to power 16 also. 2 raised to power 16, it 65535. Okay, 0 to, so it becomes 65536 individual components because 0 is also included. So what is the advantage of this? Obviously, they will be costlier, they will be more difficult to make, but more the number of levels, higher the resolution. Now, resolution is not only spatial. Spatial resolution we have already discussed. Like, for example, this is a ground surface tree. We know, we have already understood that the radiance, the image that is being created ultimately will be in the form of pixels. So, if this is a ground surface, how many pixels is the satellite or the sensor classifying it into? This corresponds to spatial resolution. Then there is a resolution, type of resolution known as spectral resolution. We have already studied electromagnetic spectrum, various wavelengths. Okay. The ability, higher the ability of the sensor to detect different types of wavelengths, higher the spectral resolution. Then we have temporal resolution. Again, the easiest way to remember is, already know one word, resolution. Resolution, take it apart, temporal, spectral, spectrum, wavelength, spatial, ground, on ground, space, temporal, time. It determines the frequency of visits. So some satellites like MODIS, they have low spatial resolution as compared to Landsat, but high temporal resolution. That is, they visit a particular area on the planet Earth more times as compared to Landsat. So some, if you want regular reconnaissance or regular monitoring, so there, that is an advantage. Then there is the radiometric resolution. This radiometric, the ability of a sensor or a satellite to detect the differences in individual brightness levels. This we are talking about. This is related to DN. Okay. Now, when we talk about DN, so DN needs to be recalibrated to reflect or to denote the actual value of radiance energy, because we humans, we don't understand DN. We know energy, joules, calories and all that. So this is converted into radiance, which we studied previously, irradiance, radiance. This actually is known as top of atmosphere radiance because it is detected here. I'll explain why this I have introduced this term. Then now, still here, the satellite or the sensor has to account for the angle of the sun, for the season, for the time of day. So this is converted into reflectance. This is still top of atmosphere. Okay. Then comes the important part, reflectance, because ultimately, if we have to study the image, we have to study, contrast the features which are present on the surface, we need a relative ratio of value. Now the problem here is that this does not reflect the actual reflectance of the values on the ground. Why? Because not only is the light, when it is coming from the sun, scattered, but also when the light is getting reflected from the surface of the earth, it is also getting scattered. Okay, so for that we have to make some corrections, like for example dark object saturation DOS. We'll not go into detail right now. So reflectance after correction, it gives SR, surface reflectance. This then actually helps in categorizing or distinguishing between the different features present on the earth's surface. Okay, so this is a little, you might be overwhelmed with it. Okay, a little bit of this. this image. I was talking about scattering. So to just lower the burden on your mind, so scattering. Redirection we have already defined. We have discussed reflection. Scattering, why it is important. So one major type of scattering which we commonly come across is Rayleigh scattering. Okay, some scientific concept behind that. Basically, Rayleigh scattering, before I explain how and why it works, Rayleigh scattering happens when the particle size in the atmosphere, which is responsible for the scattering of light or radiance or irradiance, that is smaller than the wavelength of the light. For example, oxygen, nitrogen. The molecular size of these two, which are the two major gases in the atmosphere, they are less than the wavelength of light. Okay. Now, what happens is daytime. Here, the illustration is here. So, in daytime, what happens is the sun is much closer to us. Okay. What happens is it is emitting visible light. It has various components, WebGears. Blue light is there, red light is there, green light is there. Now remember, blue light has the shortest wavelength among all WebGear. Red has the maximum wavelength. So Rayleigh scattering, it has a principle. It says that the amount of scattering is inversely proportional to fourth power of the wavelength of that particular spectral radiance. What that means is, smaller the wavelength, higher will be the scattering. Blue has a smaller wavelength as compared to red. So in the morning, it gets scattered more. It gets scattered and reflected from various surfaces. And that is why the sky appears blue. Okay. During sunset and sunrise, what happens is the the sun appears to be far away when it is near the horizon. So light has to travel a greater distance, a greater portion of distance through the atmosphere. So blue already, which is being scattered so much, it goes out of picture. It means it gets scattered so much that it does not have the ability or overwhelming power to showcase itself that boss I am present. Okay, so there the higher wavelength colors like orange or red, they become more pronounced. Okay, so you can go ahead and study more such type of scattering. There is mice scattering with aerosols. Okay, then there is non-selective scattering, the reason why the clouds appear white. Okay, so this but Rayleigh scattering is very important. Okay, so solid angle we have already studied, and why there is a need, why in the formula we have steradian. Okay, so basically we need a three-dimensional angle. There is a field of view, instantaneous field of view, lot of concepts. We are not going to go into that. Okay, now another interesting concept, spectral profile. Okay, so I'll be putting timestamps in the video below so you can skip to a particular topic if you are already aware of it. So now we have discussed electromagnetic radiation, spectrum, pixel resolution, everything. Now again, spectral profile. Like I ask, like an interviewer asks, what is your profile? What is your biodata? So again, you divide into two parts. Spectrum. Spectral refers to a particular wavelength. Okay. So boss, the interviewer asks the red wavelength, what is your profile? So he says, I reflect the sunlight or electromagnetic radiation in particular areas differently. So in one line, the representation of the unique characteristics of reflectance of a particular wavelength is known as that wavelength spectral profile. Okay, or we can say that if there is vegetation, there is building, there is water, there is sand. So each of these will reflect the various electromagnetic, the components of electromagnetic radiation at different levels. One component might reflect red wavelength more, other component might reflect green component or NIR more. Okay, so the best example to understand this, best illustration is to understand the spectral profile of vegetation. Okay, and I'll give you an example, good example also. So here, let us see. I want to draw the diagram myself, but it will take a lot of time. So here you can see now why I intentionally told you to notice the wavelengths like 380 to 750 nanometers. Now you will realize that here. So here you can see this is the visible part. So here 0.4, 0.6, this is in micrometer. So we had discussed the visible range from 380 nanometer to 750 nanometer, which is essentially 0.38 to 0.75 micrometer. So this is 0.4 to 0.75. So how does vegetation behave? It is not under my control. I am not telling vegetation how to behave to or reflect the light. Here, this is, let's consider this, the blue part, shorter wavelength. Blue part is not reflected much. Here you can see the reflectance value. What is reflectance? The proportion of energy which is reflected by a particular object as compared to the energy incident on it. So here if we say that, here it is mentioned in percent, not ratio. So here if we say that, okay, here reflectance of blue is 2 only. So it means that if 100 watts are falling of the electromagnetic radiation is falling on vegetation, it will reflect only 2% of the blue light. Okay. Then green, it will reflect relatively more by chlorophyll green pigment. Red, it will reflect less. Okay, so here the visible spectrum is over. Next, what was the next? It was near infrared, a component of infrared. So what was the range? 750 nanometer to 1400 nanometer, or 0.75 to 1.4. So this is near infrared. Now vegetation has a specific special property that it reflects high reflectance value in this region. So out of the electromagnetic radiation, all the wavelengths if we consider, vegetation reflects this wavelength the most. Okay, so this is important. Why? Because higher the reflectance value in a particular wavelength, higher will be the brightness or intensity of the radiation that reaches the sensor. So the vegetation, we will be out of various, because this is just profile of vegetation. Building will have different profile, water will have different profile. So some specific characteristics of that spectral profile, they are standing out for some objects. So if we recognize that, we can say, boss, this is vegetation for sure. Okay, so this is, then we come to SWIR. Here, what was the range I told you? 1.4 micrometer to 3 micrometer. Okay, so here it shows some non-uniform reflectance. It is basically proteins, lignin, cellulose, water content, atmospheric water absorption bands. So this is not a very reliable. This is reliable in case of buildings. We have some indices like NDBI, NDVI, NDTY. So we are not discussing that. It will be too much. Here, one important term you can notice, red edge. What is red edge? Because just like the edge of a cliff, you can see when the transition of this representation graph is taking place from red wavelength to NIR, it is showing a sharp spike. So it is known as the red edge. If a vegetation is stressed, it is affected by some disease, it is sparse, it is not healthy. So this graph will shift towards the left. Okay, just remember this for now. Okay. Finally, the what we have studied till now, all this, especially this, what is the importance of this? So you might have heard of two types. This is obviously this is a combination of images of different bands that I have downloaded from USGS. In this case, I've downloaded for Copernicus Sentinel. And fortunately, these diagrams came out to be very beautiful or nice. Here, clearly, you can distinguish the figure. That is why I am showing you. So, here, there are two types of basic composition of bands. Like I said, I didn't tell you bands exactly. Bands are basically, we have discussed the spectrum, we have discussed the various wavelengths. So bands are basically group of particular wavelengths. Now, if we consider the color red, it is not necessary that it is restricted to only one particular discrete value of wavelength. It will come in a band. Multiple values will make a red band. Other values will make a blue band because there are plenty of variations. Okay, blue has plenty of variations. Red has, it is a transition from in WebGear from violet to, so violet can also be is a darker shade. The basic colors are RGB, red, green, blue. Okay, and the bands which the satellite captures, there are a lot of bands, aerosol bands, but basic bands which we require to form image are the blue, green, red, NIR and SWIR also. But these four bands are sufficient for creating TCC and SC. True color composite, as the name suggests, bands, we are assigning the band to the respective color channels. So in Sentinel, if you see here, I have made the legend. Clearly, you can see in Sentinel what happens is red band or red color is captured, is named band 4. So I have assigned red color to the red channel. This is actually I've created in QGIS, Quantum GIS. Then green I have assigned to green channel. Blue I have assigned to blue channel, no variation. So here you can see, I think it is clear to you, here green vegetation. It is actually a representation of Eastern Ghats. This is Visakhapatnam city in Andhra Pradesh. So this green. Then you can see these bright areas, combination of various colors. These you can clearly identify as settlements, the urban areas. You can identify some this water bodies also. You can identify roads. Okay, you can identify airports also. You can identify the coast. This is the Bay of Bengal. Okay, now, but look at this image. Not just for the sake of beauty, but this is where that vegetation, the spectral profile of vegetation comes handy. It is particularly useful. Now, what I have done is I have manipulated the color channels to create false color composite. What I have done is I have taken band 8, which represents NIR in Sentinel 2A. I have put that in red channel of QGIS. I have put band 4 red into green channel, and I have put 3 which represents green into blue channel. So I have manipulated. I have not assigned the actual colors like I did in this. Now what we have studied here, that vegetation produces the maximum reflectance in NIR. So see here it was appearing green because that is a true color of vegetation. Okay, how it appears to the naked eye. But here it is appearing red. Why? It is not actually the red that is being reflected. It is the NIR. What is happening is because NIR, we cannot see NIR. It is out of the visible range. NIR I have assigned to red color. So wherever this color was being reflected in the red, in the green, in the vegetation, it is now reflecting in the red channel. So here it is reflecting NIR, but I have said, I have told or instructed QGIS or the software to show the area, to show the NIR area in the red color. So that is how we identify. So here you can see there is no blue. Okay, but a combination of colors. So you can see we have water bodies are appearing dark, normally very dark blue or dark, like black, violet, because out of all these bands, water We have already discussed the reflectance. Water already reflects very less, and a few bands. Then this here, the settlements, they are normally gray or cyan in color, the dense settlements. So this I have specially illustrated from the point of view of vegetation, and from the shadow which is being generated. These are the elements of visual representation: tone, texture, association, okay, color, pattern, size. So you can see that this vegetation is on hills. It could have been agriculture also, but how to distinguish? Agriculture also gives a reddish tone in FCC, but here you can clearly see by the shadows here also that these are vegetation in hilly areas, and it is dense vegetation. Okay, so I think that is enough for today. I hope that the lesson was beneficial for you. So till we meet again next time, Jai Hind.